Okay, I accidentally just closed my lesson, but I can start it right up here. And if you close a lesson but you don't shut down your notebook server, it will just pick up where you left off. So we just finished with the moon stuff. And now we're going to do some other statistical tests that you might want to do, right? So if you have two nominal variables and you want to see if the proportions are the same, you can use a Fisher's exact test. If there's a small number of sample sizes, you can get the exact probability that the proportions are the same in these two groups. So this would be used for less than 1,000, and I've put some examples here. This is all from a handbook to biostatistics, which I will make a note. By the way, this table is all generated using Markdown, so you just use this simple format here to add in the table, and it's this. This is the link is really nice web-based book on biostatistics that's free. And I can add in a link here in Markdown format. And as usual, you don't need to add this. I'm going to update the GitHub afterward. Okay, so he just gives you a couple. He just gives you a add his name here. He gives you a couple examples. So, for example, counting the number of patients who live or die after treatment with a drug or placebo. And if you have a large sample set, you can approximate that using a chi-squared test. So again, this is not a statistics class. I'm just showing you some examples of what you might want to do and how Python can help get you there. So, Fisher's exact test is when you have two nominal variables and you want to see whether proportions of one variable are different depending on the value of the other variable, and used when samples are small. So we can get the information about that if we want. You just have to convert that to a code cell and then execute it. So it takes two parameters. It takes a table, and then optionally you can say whether you want to do a two-sided test or less or greater than. I'm going to do two-sided, which is the default. And the example we have, which is actually provided in the help documentation, is that if we are counting whales and sharks, which is something we might do here at Scripps, in the Atlantic and Indian Oceans. In the Atlantic Ocean, we find 8 whales and 1 shark, and in the Indian Ocean, we find 2 whales and 5 sharks. So we make this contingency table where we have our indexes are our study sites, so the Atlantic Ocean and the Indian Ocean, and the columns are our observations, either whales or sharks. And so we have this pandas data frame. We can then use the SciPy stats Fisher exact test on that data frame. We're going to do a two-sided test, and this gives us an odds ratio and a p-value. So the probability that we would observe this or an even more imbalanced ratio by chance is about 3.5%. So this falls below the common significance level of 5%, so we might conclude that whales are more common in the Atlantic while sharks are more common in the Indian Ocean. So we can do that same test using a chi-squared test of independence. This is the same kind of test but with a larger sample size, and it takes observations like the contingency table and gives us back the chi-squared statistic, a p-value, number of degrees of freedom, and the expected frequencies if the just if there was no difference in the distributions. So so we can just run that table, and we get this test statistic indicating that there's a observed distribution is skewed from the expected distribution. So there's also a number of tools available for doing analysis of variance. So this includes ANOVA, but also more simple special cases like T-tests. So, and this is all again provided by SciPy Stats. So, a one sample T-test is testing that whether the null hypothesis is that the expected value or the mean of a sample of independent observations is equal to a given population mean. So we give an array, so a set of observations, and then a mean or an expected mean. So this is testing whether the mean is likely, how likely is that mean given the observed data. And this gives us the t statistic and a p-value. So we can go back to this moon diameter data, and we can say that, okay, so the population mean, when we exclude the outliers, which is the Earth's moon, is approximately 0.18. And so we can just calculate that mean with the outliers removed. And if we say that, okay, what is the sort of, how likely is it that we can reject that the expected mean of 0.02 is equal to the population mean? The t statistic is rather low, and the p-value is quite high. So we can't reject, and this makes sense, right? The 0.02 is quite close to 0.018. So if we said, okay, the mean is 0.02, like, yeah, that's a likely mean for this data set. However, if we assume that the Earth's moon is normal, is representative of this data set, so if we said the Earth's moon with a ratio of 0.273 relative to its host planet is the mean, and we look at all these other data points, we get a very strong p-value saying that there's no way that that the mean, if we assume that the Earth's moon was the mean value of a moon to planet diameter, there's no way we could make that conclusion looking at all these other data points. So a two-sample t-test is a test for the null hypothesis that two independent samples have identical average or expected values, and this assumes that the populations have identical variances or have homoskedasticity. So we can learn more about this test with this command, but basically what this just tells us is that we have two main parameters, A and B, which are arrays, and then optionally, if we have multiple axes in these arrays, so let's say these are data frames, we could specify which axis we want to compare along, and then this is going to give us the statistic and the p-value. So in this example, we're going to create some random arrays. We're going to make one that's a normally distributed random array of length 40, and then we're going to make another randomly distributed array of length 50. We're going to increase the amplitude of that by 1.5, and we're going to add 2 to it. So these should have these should have different means. And we're going to set a random seed so that you and I all get the same values. Okay, so we then use this scipy.stats.ttest for two independent samples. Those two independent samples are A and B, and we say that no, they don't have equal variance because the way that we've set this up, they don't. So this will give us the t-test, the t-statistic, and the p-value. So using these assumptions, we can tell that they have significantly different means. There's other ways that we can compute. So we can directly compute the descriptive statistics of A and B, and then run a test where we provide those stats directly. So let's say there might be an example where we didn't have access to all the data, but we knew what the underlying statistics were, or the summary statistics were. So we can calculate the mean, the variance, the size, and the degrees of freedom of A and B. And then we can generate the same statistics, but this time we're using a different function, which is t-test of independent observation from stats, where we provide A bar, which is the population mean, the square root of the variance, the number of observations, etc., for those two series, and then we're going to print the output of those calculations, and we can see that we get the same values. And we could also generate those data using the formulas directly. And finally, we can just confirm that what we got with the statistics matches up with what we can see visually. So we can use the Seaborn dist plots to look at those two distributions, and it makes sense that those means would be different. We can see that there's nice separation between those two data sets. The last function with analysis of variance is the actual ANOVA test. So this is testing the null hypothesis that two or more groups have the same population mean. So this is sort of a more generalized case of a t-test. And so we pass in an array of samples, and it will return a test statistic and a p-value. And just note that the normal assumptions of ANOVA must be met in order to use this test in order for the results to be valid. So the samples need to be independent. Each sample needs to come from a normally distributed population, and the population and standard deviations should be equal. So they should have homoskedasticity. And if the assumptions are not true, you may still be able to use the Kruskal-Wallis test, which is also available with SciPy. Okay, so there's some data that are available. These are data that were cited by this Handbook of Biological Sciences, actually, in the example he gives for ANOVA. And these are shell measurements of the muscle middleus trocculus from 5 locations along the Pacific coast, and also Russia and Finland. And this is just a subset of data. So these are just arrays, or rather just lists of values. And from those, so we create lists of those values. Of course, you could also import these as CSV file, but yeah, here we'll just supply them directly. And then first we're going to look at a dist plot of those 5 series. So this is just using Seaborn defaults with colorblind friendly colors, and we're labeling them accordingly and then putting a legend in there so we can see that it looks like there are some differences in the means of those values, but we're going to do a one-way ANOVA to test for that. So we simply provide the function scipy stats f one way and then pass those 5 lists to that function, and it gives us the ANOVA statistic and the p-value. So this shows us that these means were significantly heterogeneous, and the way that we can represent that when we're reporting it is state that we did a one-way ANOVA with this f statistic as 7.12 with these degrees of freedom and a p-value of 2.8 times 10 to the minus 4th. And if we had done all of the normal ANOVA calculations, we could generate this table of degrees of freedom and sum of squares and so forth.